last aspects of workability, that is what we are going to discuss today, are segregation and bleeding. So far we have looked into workability with reference to fresh concrete. So, this is the last aspect of fresh concrete are segregation and bleeding. These are two phenomena which takes place in fresh concrete. So, we shall first look into segregation. We will discuss about the mechanism, something about the test, possible test for segregation, and then what factors affect segregation. Then we will look into the other phenomena, that is bleeding, and then we will look into its mechanism, test, and what factors affects or how we can control bleeding. That is what we will look into. Right. So, let us start with segregation. Let us define it. Well, we have seen through several of our earlier lectures that concrete from the time of mixing and finishing, it is subjected to transportation, placing and compaction, and during this process it must remain uniform, right. During this process it must remain uniform. If it does not remain uniform, then we call it to segregate. Does not remaining uniform implies that ingredients are separating out, and that is what we call as segregating. Well, results, some of these results we have earlier seen, namely we have seen there is something honeycombing that takes place, that could be the result of segregation, because the coarse aggregates remains and the fine aggregate are separated out from them, and that is what is one kind of segregation. It can result in honeycombing, and in general this can result in low performances, right. So, that is what is the results of segregation. Then this is, therefore, if we define it, is the process by which well mixed concrete, a well mixed concrete, fresh concrete becomes non-uniform within a batch. So, in a batch which you have mixed properly to get a uniform concrete, this process of segregation is the process by which the concrete will become non-uniform. It will become non-uniform for the same batch, and it may mean variation of coarse aggregate content at places. Basically, you see, when we are talking of segregation, this phenomena essentially means that coarse aggregate content would vary, because the ingredients, they are non-uniform now. So, in some places you will have one material, some other place other material. Since aggregates are the large part of the material, bulk of the material is the aggregate, and that too the coarse aggregate forms bulk of the volume of concrete compared to other ingredients. So, quite often the proportions of coarse aggregate in one place would be different than other place when it is segregated. So, segregation results in coarse aggregate proportion being different at different locations. So, that is what we are saying, that is how we define segregation, right, that is how we define segregation. Okay. So, that is how we can define segregation. Then let us see what are the types of segregation. Two types of segregations are defined. One is called internal segregation, where coarsest or heaviest part of the aggregate tends to accumulate at the bottom, you see, tend to accumulate at the bottom, and lighter, and if it is usually the finer ones, that tend to accumulate at the top of the mix, usually during compaction. So, you have a section of the concrete, let us say, and the bottom will have heavier, in the bottom will have heavier aggregates, right, bottom will have heavier aggregates, this portion, and the top aggregate would tend to accumulate at the top, top. So, this is lighter, this is light, this is heavy coarse aggregate, usually coarse aggregates are heavier, and when this happens we call it internal segregation. Usually the aggregates, the coarse aggregate which are heavier will have a tendency to settle at the bottom compared to the lighter finer aggregate and mortar containing the finer aggregate, that will have a tendency to set. So, that is the results of an internal segregation as opposed to external segregation. Now, external segregation, if you look at it, that is due to some sort of external forces, say improper handling, and this we have discussed earlier. We have seen that if you do not discharge a concrete from the mixer in the right manner, then large size aggregate particle may be placed somewhere, whereas the fine, like for example, is a drop from a very height more than 2 meter, or dropping directly, or through an inclined very steep slope if you are dropping it, or the bottom opening is very small or inclined, etc. Several of them we have discussed earlier. We have seen this when you are not handling properly, it can result in segregation, because larger particle will have a tendency to move away from the discharge point, and the mortar will have a tendency to settle very close to the discharge point, and that is kind of segregation we have looked earlier in one of our earlier discussion in the context of placing of concrete and handling and placing of concrete. So, external segregations are results of such handling, improper handling, such improper handling, right, or due to compaction, in vibration, etc., those kind of thing can also lead to external segregation. Okay. If you have inadequate cohesiveness of the cement, let us say high water cement ratio. So, you do not have sufficient, you remember that we said that cement paste shall be cohesive because it is supposed to disperse the aggregate. It forms a matrix and in which the aggregates are dispersed, and then it must have the therefore, it must have the dispersion capability, and it must have also the capability to hold it together. It should be sufficiently cohesive. But supposing we have high water cement ratio, it is thin, the paste itself is thin and not able to hold the system properly, it can result in water just flowing away, it is too thin. So, water just goes away alone in the mix, leaving the rest of the thing, and therefore, this can result in what is known as wet segregation, If you have insufficient water cement ratio, that means now it is not again it can't hold the aggregate, the paste cannot hold the aggregate because the water is less, it is dry. This may result in dry segregation. So, what will happen? This can result in, usually these are external segregation, external segregation while handling. So, this could dry segregation. So, the stones, etc., will go away, the coarse aggregate will go away, leaving the dry mortar close nearby at the discharge point. So, this can, wet segregation and dry segregations are the other two, and these are variety of external segregation. So, this is what are the types of segregations, right. This is the types of segregation. Why does concrete segregate? Mechanism of segregation. If you have density of the aggregate different, you have different densities of the aggregate, say coarse aggregate has got a different density than the mortar, then internal segregation can occur. Because we said that what is internal segregation? The tendency of the coarse aggregate which are heavier has to settle down at the bottom, and the finer mortar which has got actually fine aggregate with specific gravity is different will have a tendency to relatively remain at the top. So, when you are compacting, if something heavier will have a tendency to go down, something lighter will not go down so easily, it will have a tendency to remain at the top. And if the specific gravities are significantly different, say in case of something like heavy concrete is used in radiation shield, hematite is used as aggregate which could have a very high specific gravity order of 4, 4.5 and so, and if you use as finer aggregate or mortar which has got much lower density or specific gravity of the sand is very low, this can lead to the sand remaining at the top and the mortar remaining at the top and aggregates going down and result in internal segregation. So, internal segregation can occur when there is a specific gravity difference between the two, because it is internal, it is not due to any external agents, not due to handling, just because the specific gravities are different, aggregate would have a tendency to remain separate than the motor, right. Okay. Let us see what could be the other one. In case of jolting and vibration and other forces, dissimilar ingredients may get separated. Now, remember when we were talking about conveyor belt sometime, transporting concrete through belt conveyor. So, when you are transporting concrete, let us say through belt conveyor, you have jolting, when you are trying to transport concrete through belt conveyor, you can have jolting, you can have jolting, so over the belt rollers it can jolt, because you remember we had belt something like this, the belt will travel like this, and when this concrete on top is the heap of concrete travels through this, it will have a jolting, it travels, concrete is placed here. So, over the belt conveyor, this is the direction of the travel of concrete, it can be jolting, there can be jolting of the concrete. So, in such situations, since the concrete is being jolted up and down, so it can so happen that the larger particle moves in a different way. If the cohesiveness of the mix is not proper, larger particle moves, does not move, it moves more, the mortar remains sticking to the concrete. So, if you have too much of aggregate in the system, such a thing can happen. So, similarly, vibration can result in dissimilar aggregates, ingredients, that is aggregates and the mortar dissimilar there, both in shape and sizes, may get separated, they might get separated. So, jolting etcetera can result in jolting and vibration, that is external. So, that is the mechanism of segregation. The factors affecting internal segregations are the friction, internal friction and bond, and friction between paste and the aggregate, the cohesiveness and ability of the plastic deformation of the paste and mortar, and interference between coarse aggregate particles. That means, what would stop segregation? If the aggregate is held in position, by or in its location by the paste or within the paste, because the paste forms the matrix, aggregates are dispersed within that. And if we see slightly ahead, the mortars forms the matrix and coarse aggregate particles are dispersed in that, embedded, or you can say they are dispersed in that, their inclusions sort of dispersed in that, because they cannot, just not embedded, they are large quantity. So, they are dispersed in the mortar. Now, if the mortar is cohesive, it is effectively dispersed in the aggregate system, then it will be uniform, but it must have also the holding capacity, should form proper bond with the aggregate, should have the right kind of holding capacity of the aggregate, so that there will be no segregation. So, if this bond is not there, there will be segregation, and that is being talked about, right. So, this acting is an internal friction, right, that is a bond, and friction between paste and aggregate. So, this is what it is, and this bond is one thing plus friction. So, if something is moving, the friction would oppose that movement. So, friction between the paste and the aggregate system and mortar and the coarse aggregate system, right, the cohesiveness of the paste and the mortar and ability to plastic deformation. Now, if it holds, then plastic deformation of the mortar and paste to take place, and simultaneously it will also cause deformation of the or movement of the aggregate together with it, and that is what actually will stop. If this is not happening, then there will be segregation. So, these are the resistances, or you can say these are the factors affecting the against internal bleeding, internal segregation. So, the factors affecting factors which opposes the internal segregation are the bond, the cohesiveness, the friction between paste and the rest of the aggregate, mortar and the coarse aggregate. So, therefore, all this can resist. This is not internal friction, this should be internal segregation, So, internal segregation internal segregation can be resisted by cohesiveness of the mix. So, if the mix is cohesive, and you can see this all points out, if you have a good workable mix which can deform easily, would actually give you proper resistance against segregation, right. So, that is the mechanism of segregation, and that is how we can see that what opposes the segregation, right. Continuing with the mechanism of segregation, you see, as I mentioned, all the above factors points out to the fact that, it points out to the fact that workability has got a strong role. If you have a good workable mix which is capable of deforming and move uniformly, cohesively, this will actually resist segregation. So, strong role, thus a workable mix is less prone to segregation, that is the idea. So, workable mix, properly workable mix is less prone to segregation. Segregation means separation. So, something has to, the paste has to hold the aggregates, the mortar has to hold the coarse aggregate, and then there will be no segregation. So, if the mix is that, there will be very little internal segregation. Right. This is what is being reiterated, the ability of the mortar to hold the coarse aggregate and disperse them adequately, resist segregation. This is very important. This should be understood, that mortar should be able to. So, mortar itself should be cohesive and sufficient enough to hold the coarse aggregate in position. So, quantity of these proportions are important in that respect. Cohesiveness of the mix is most important, together with appropriate handling method, because we have seen that if you handle it in a wrong manner, if we have seen earlier sometime that if you handle it in a wrong manner, like the bottom opened bucket, that does not, and wide open bottom opening, bucket with wide bottom opening, they do not cause segregation. If you have a batch, part of the batch loaded on a wheelbarrow and another part is loaded onto the another wheelbarrow, this will have definitely sort of segregated mix. Similarly, when you have two stiff chute through which you are discharging the concrete, that can result in segregation. Dropping the concrete over height more than 2 meters, those can cause segregation. So, similarly, jolting over the conveyor belt or transporting concrete through simple truck over a undulated road, all this can result in external segregation. So, appropriate handling is very, very important, and also the mix, right. Okay. How do we test? One of the tests that was there earlier, or because there is not really, these tests are yet to be standardized. One of the tests proposed was that you have a cylindrical concrete mold, something like this, you have a cylindrical concrete mold, right. Fill this mold with concrete, in a specific manner and vibrate it for a fixed time, then separate it out into two parts, the top part and the bottom part, bottom part. Right, upper and the lower part. Then what you do? You measure the proportion of quartz aggregate in this portion, upper half, and proportion of quartz aggregates in the bottom portion, right. So, you measure the proportions of aggregate in two halves. Then the segregation factor is defined as, this is SF is called segregation factor, which is the ratio of quartz aggregate content of the lower part to the quartz aggregate content of upper part. We have separated into two parts. If you remember last slide I was just talking about, this is the upper half, this is the lower half, and quartz aggregate content is measured in two halves, and if the ratio of the quartz aggregate to the lower part to the upper part, that is called segregation factor. So, if it is not segregating, if it is uniform, this should be equals to 1. So, 100% non segregating mix will have this equals to 1. Lower, close this value of SF to 1, the tendency of internal segregation will be least. Tendency of internal segregation will be least when this is very, very close to 1. So, this is one method and a very simple method of measurement of segregation. Tendency, segregation tendency against internal segregation. So, SF is a measure of internal segregation. Closer it is to unity, the milder is the tendency of segregation. That is what we have understood, that closer it is to unity, milder will be the tendency to segregation, internal segregation. This will happen if you have specific gravity difference between the quartz aggregates. So, you have vibrated it, if the quartz aggregate is very heavy compared to the mortar, it will go and settle down at the bottom, and that is what we said is the cause of internal segregation by and large, because internal segregation means the aggregate proportion should be different in different part of the concrete, right, different portion of the concrete. So, and one of the major reason is this. For external segregation, uniaxial tensile strength is a good measure of tendency of external segregation, higher tensile strength have less tendency. This is what we talked earlier also when we were talking about rheology of fresh concrete. When we are talking about rheology of fresh concrete and paste, etc., we mentioned that 3 components in terms of workability of concrete. There are 3 terms, if you remember. First one we said was compactability, second one is the mobility, third one is the stability. Stability means it does not segregate, especially under external handling, vibration, etc., etc. So, this it will not segregate if the tensile strength of the fresh concrete is high. So, uniaxial tensile strength is a good measure. There are some ways to measure this, against external segregation. Higher tensile strength have less tendency. So, it is actually if you have workable mix will have less tendency to segregate as well, because it will have sufficient cohesiveness to hold on to the quartz aggregate. The mortar will have sufficient cohesiveness, it will be of sufficient quantity to hold the quartz aggregate in position and also disperse them, right. The other test, so external, this is the uniaxial tensile strength, and that is, you remember, this is related to workability. So, good workable mix are generally less tendency, they have less tendency to have segregation. Now, other test is called heap test. A heap test is, there are several other tests proposed, but I just picked up one more simple test. In heap test, the concrete sample is allowed to fall from a conical hopper on a flat surface, and after setting it is photographed. So, it is a very simple method. You have a standard conical hopper which is same, use the same one for all concrete, and it is allowed to fall through it to a flat surface over a standard height, over a fixed height, I mean I will not say standard, but fixed height, and is observed through photograph after setting. And this photograph is observed for tendency of external setting. For example, when you have dropped through this hopper to the flat plate, the concrete, if the quartz aggregate particles are separated off there, if the quartz aggregate particles are separated off there somewhere else quartz aggregate, and the mortar forms as a hip, mortars something like forms as a hip here, mortars are something like hip, and aggregate particles are separated off, then it has a tendency towards external segregation. Supposing nothing happens like this and all concrete are forming as a heap of this form, then it has got less tendency to external segregation. So, that is how we can measure the external segregation as well as internal segregations, tendency. So, tendency to segregation, but these are not usually, these are not very often done. When doing in laboratory studies, one may do it to find out, because it is not possible to do day in day out in a quality control situations. But this is how one can test whether it has. One faces the segregation problem if the mix is not proper. Visually you can observe whether segregation is taking place or not, and of course, one has to be careful as far as internal segregation is concerned, when specific gravity of aggregates are quite different. Okay. But otherwise, well, one has to just check it. So, these are meant for laboratory testing, not really quality control test. Right. Let us see what are the factors which affects the segregation, and these factors are, if you have large size aggregate, maximum size of aggregate, nominal maximum size of aggregate over 25 millimeter has a tendency to segregate more, because the larger the size, this has a tendency to go away from rest of the thing, and higher quantity of large size particles, or there is something called gap grading. Gap grading. Now, what is gap grading? We talked about grading in the, sometime we said grading, we talked about grading. What is grading? Grading is having different sizes in right proportion. Supposing one of the size is missing, one of the size has got 0, it can happen, and one can design good concrete with that as well, but one must keep in mind what are the possibilities that can happen. Gap grading means one size in between is missing, because that is not available at the site. So, you do gap grading, if you do gap grading, right, if you do gap grading, now such gap graded system will have a tendency for the larger size above the gap to move away, because you see gap graded means one particular size in your grading is missing, because we said the final next size will go inside this, and the next size will go still inside this in the finer size, and so on. Supposing one of the sizes is missing, the cohesiveness of the mix would be there inside may be relatively less, and holding capacity might be less. So, the larger size aggregate will have a tendency to go out, but that does not mean you can't have gap graded concrete. You can have, ensure that you have cohesiveness of the rest of the mortar or rest of the mix, having sizes that contain sizes finer than the largest size. So, one can still design, there is no problem. The other issue is of course the specific gravity of the coarse aggregate relative to the fine aggregate. This is very important. So, when all these are there, you have to look for measures to reduce down the segregation tendency. Low fine aggregate fraction in the sand and low cement content. So, also unfavorable shape of aggregate and too dry or too wet concrete. Now, these are the factors which affect the segregation. Now, that means if it is gap graded, if you have this sizes larger than this, it does not mean that you can't make concrete without them. What you have to do is possibly you have to increase the fine content, maybe you have to increase the paste content and cement content, and makes the paste cohesive and its holding capacity more. Similarly, high quantity of large size particle, if it is there and gap grading is there, you have to again possibly increase the fines or paste and increase the cohesiveness of the paste to hold this one. Specific gravity difference, if that is there, then again you have to see same thing, maybe the large size aggregate, maybe quantity can be reduced and you increase the mortar content relatively more, so that it can hold and disperse. So, accordingly one can design them, one has to keep this in mind. Since we know these are the factors, low cement content is a factor, so we might have to increase it, low fine is a factor, so we may have to increase it, and then unfavorable shape of aggregate, if it is there, maybe you have to increase all this, we have to increase all this, maybe we have to increase all this. Too dry or too wet mixes that we talked about, that means water cement ratios are to be checked. If I have too dry, less or too water cement ratio, there has to be other measures by which we have to actually reduce down the segregation. So, that is how one can control the segregation if one knows factors affecting. Well, that is I think all about segregation. All right. One additional thing is that air entrainment can usually reduce down the segregation. How does it do it? Because in when you use air entraining admixtures, air bubbles are formed uniformly throughout the structure. It is very uniform throughout, and it maintains, this air bubble maintains cohesive mix, maintains the mix, the paste cohesive, and therefore, it can hold on to the aggregate system better. So, by increasing the cohesiveness of the paste system, and then of course, the mortar system, because paste is included in the mortar, or that forms the sands are dispersed in the matrix, paste matrix. This can improve the cohesiveness of the overall mortar, and then allow, maintain, or rather can contain the aggregate within it in a dispersed form, hold it together, and therefore, air entrainment can lower the segregation. Right. So, that is all about segregation. Let us look into the next aspects of the fresh concrete. So, segregation tendency has to be reduced. The other aspect, similar aspect, is bleeding, bleeding of segregation, I mean bleeding of concrete. Bleeding is nothing but a special case of segregation. Segregation perhaps is a general term where ingredient separates out. So far I have been talking about separation of the coarse aggregate from the rest of the material. That means, it is the aggregate system which can separate out from rest of the matrix, rest of the concrete system. Bleeding is where water gets separated from rest of the material. So, generally segregation is separation of the material. In that sense, bleeding is also part of overall segregation. Okay, let us define bleeding. Right. Now, after compaction, when plastic concrete stands without agitation, we are not vibrating it anymore, water appears at the surface. This emergence of water at the top from freshly placed concrete, paste or mortar, we call it bleeding. It is also called sometimes water gain. So, after you have compacted it, the concrete, when it is standing alone without any agitation, till it is set, what will happen? Water generally tends to come up at the surface, and this tendency of water to come up at the surface and accumulate, we call it bleeding or water gain. I have already mentioned bleeding takes place prior to setting. Now, we can identify two types of bleeding. You see, one is called uniform bleeding, other is called channel bleeding. We can identify two types of bleeding, one is called channel bleeding, other is called uniform bleeding. What is uniform bleeding? It takes place by uniform seepage over entire surface. So, water comes up at the top, that means there is some seepage of water from the fresh concrete, the green concrete, it is also called green concrete, fresh concrete, it is a fresh state, wet state, the water comes up. You can understand that this is easily understandable, as we shall see later on. The specific gravity of the materials in concrete, the ingredients of concretes are different, and water has the least specific gravity. So, it generally tends to come up, it seeps through, and when it is uniformly seeping through the entire surface of the concrete, right, this is called uniform bleeding, this is called uniform bleeding, right. Okay. So, this is called uniform bleeding. But sometime what can happen, in addition to this uniform bleeding, some places the water might come out selectively, very high rate, at a very high rate water might come out selectively through some channels that is formed, localized channels formed, and this is called channel bleeding. These are called channel bleeding, right. So, two types of bleeding we have recognized, one is uniform bleeding, other is channel bleeding, right. Okay. So, what is like this is your, let us say, okay, this is let us say this is my concrete, this is my concrete, let us say this is my concrete, right. So, when this is my concrete surface, when water comes up throughout uniformly, that is uniform bleeding. But sometime you might see that water comes out uniformly, all right, but some place there are some places water is trying to come out more and getting dispersed all around. So, this place it is water is trying to come out more, rest of the place is relatively dry, this place is wet and water is trying to spread from these places. So, channel bleeding, because some channel might have formed inside through which the water is coming, seeping through at the top, and that is called channel bleeding. So, channel bleeding is localized through channels and uniform bleeding is all over the surface, right. Now, when water comes up, you have bleeding and the solid subsides, because overall volume is same, total wet volume contains the solids and the water. Now, water is coming up, water has come up at the top, this was the original total volume. Now, water you will have here, and the rest of the solid is there. So, the solid would have subsided, the water would have come, and that is what is, that is what happens in case of bleeding. So, solid comes, total volume remains same if there is no evaporation loss. So, if there is no evaporation loss, total volume will remain same. When there is no evaporation loss, total volume will remain same, when there is no evaporation loss, total volume will remain same, right. So, in case of bleeding, total volume remains same, but if evaporation takes place, actually there is a decrease in volume. Okay. Now, therefore, bleeding can be quantified in terms of subsidence as well, because the volume is changing, that is one thing, and second thing is there is a subsidence. So, when we want to quantify bleeding, we can quantify bleeding in terms of subsidence that is taking place, subsidence quantified in terms of subsidence, and can also in terms of volume of bleed water. So, we can quantify either in terms of subsidence or in terms of volume of bleed water, that is there. So, this is the two way we actually quantify bleeding. We quantify bleeding in two different ways, one in terms of subsidence and second in terms of volume of water that has come out. We quantify it in terms of in three ways actually, and that is what we will be mentioning in the next slides. But let us understand a little bit about how the bleeding takes place. Right. You can see I mentioned the specific gravity of ingredients are different. If you see cement, the specific gravity is 3.15, which is the highest. I think I am repeating this, I must have mentioned earlier, and this one must realize in concrete the cement has got a specific gravity of 3.15. The specific gravity of normal aggregate would range from this, but sometime it can be higher also depending upon the minerals or mineralogical composition of the aggregate. For example, if you are using iron ore as a aggregate, then obviously this will be much higher. But cement is normal OPC cement is around this, and water has got a specific gravity of 1. So, you can see the water is the lightest of all, and this is inherent to concrete. Water will have a tendency to come up, water will have a tendency to come up. So, these are your aggregate system etc. in the mortar, water will have a tendency to come up, and when it comes up, it brings in some amount of cement slurry also with it, if especially very fine particles, they can come together with the water. Even in case of uniform bleeding, some amount of slurry will come. In case of channel bleeding, of course, large quantity of slurry will come. So, this surface lattice is formed with this water which has come up, and water which has come up with the fine material, it will form a slurry. What about cement? Cement will try to go down, also aggregates because it is somewhere intermediary. But one additional feature which we will discuss again is that water might get accumulated, it can trapped, bleed water can get trapped below the aggregates, large aggregate system. So, this can be water rich pockets, and this water rich pockets have got their implications in many other things, including the strength of the concrete. So, these are water and durability as well. So, these are water rich pockets, bleed water can get stuck here. Right. So, basically why does bleeding takes place, and it is somewhat inherent. Of course, you can control it, reduce it, keep it in an keep it in a situation, keep it in a way or to that level where it is not so harmful, but water will definitely will have a tendency to come up. So, in fact, you will have higher water here and less cement. So, water cement ratio here is also very high compared to at the bottom. So, bleeding actually takes place because water has a tendency to come up, being the least specific gravity material, and cement has a tendency to go down, right. So, that is what it is, okay. And if we define, then we can now quantify what is in different way the bleeding. First way we quantify is called bleeding capacity, bleeding capacity, right, this is what we are calling. So, bleeding capacity we can define in terms of volume of water released from unit volume of concrete, total volume of water released from unit volume of concrete, during throughout the bleeding, because bleeding does not take place in one go, it takes place over a period of time, right from the time you have placed the concrete filled the mold to the time it has set, the bleeding will continue. Of course, not necessarily up to the point of setting, but setting may generally arrest the bleeding process, because once it is solidified, the water has reacted, it can't come out. So, as the setting process progresses, bleeding will stop gradually. So, during this whole period of bleeding, the duration of bleeding, the amount of total volume of water that has come in from unit volume of concrete, that is what we call as bleeding capacity, right, and it might be expressed in cc per cc of fresh mixture. The amount of cc is the volume of water in 1 unit cc of fresh mixture of paste, concrete, mortar, everything, whatever you are in the context that you are talking. Or it can also be defined in terms of settlement, because we said the subsidence is another way of defining the bleeding. So, quantifying bleeding in terms of bleeding capacity, we can talk in terms of settlement, amount of settlement divided by the original height, or settlement per unit height. What we are saying is settlement per unit height is the setting still setting arrest bleeding. So, during the total process of bleeding, the bleeding that has taken place divided by the original height, it means bleeding per unit height in centimeter per centimeter is the bleeding capacity. So, this is one way we quantify bleeding. The other way of quantifying bleeding is in terms of what is called bleeding rate. Bleeding rate is defined as the rate at which water is released, and it is expressed in terms of volume of water, that is in centimeter cube cc per second, the rate per centimeter square of the surface area, of concrete. So, it is the volume of water released per unit time per unit surface area of the concrete, or it can be talked in terms of subsidence at a point on the surface of the concrete in terms of centimeter per seconds. So, the rate at which it is subsiding at any point of time is called bleeding rate. This rate is obviously cannot be constant, it will be constant possibly for certain period of time, but it will reduce down with time. We shall have a diagram to see this. So, bleeding rate would change, but we have a way of defining. Next slide will define that in details. Okay. Now, let us look at the third way how we can quantify bleeding, duration of bleeding. It is the periods elapsed from concrete placing to that time when bleeding has become negligible, Well, in terms of subsidence, if we are looking at it, this diagram will show you how we can quantify this, right. So, you can see this through this diagram, that this diagram shows for a specific type of water cement ratio 1.32, because one would have liked to have high bleeding by absolute volume. This is by volume anyway, and the sample has been taken as 4.25 centimeter, and then bleeding was measured by what is called float method in terms of the subsidence. So, the volume is not there, it was measured in terms of subsidence. This axis gives you time. So, this gives you time in minute, and then what has been done, subsidence has been measured. So, originally it was 0, then subsidence increases along this direction 0.1, 0.2, 0.3, 0.4. So, subsidence has been measured in terms of subsidence in centimeter 0.1 centimeter, 2, etc., subsidence has been measured with time. So, when you measure the subsidence with time, it is observed that initially it has got a almost linearly it is decreasing, So, this is the period of constant rate, Then you can see that bleeding gradually reduces down, the rate of bleeding gradually reduces down. So, this is the rate of bleeding, the initial rate of bleeding, we call it rate of bleeding in centimeter per second. So, that is the rate of bleeding. The total subsidence is this, and you remember bleeding capacity has been defined in terms of total subsidence, right, per unit original height. So, this is related to total subsidence. So, bleeding capacity can be defined in terms of this. So, bleeding rate orders are given, for example, 103 into 10 to the power minus 6 centimeter per second, etc., the rate has been defined, and period of constant rate. Beyond that, of course, the bleeding rate reduces. So, duration of bleeding, which is the third measure of bleeding, is shown here. So, you can see all three quantifying terms for bleeding are defined through this curve. These are the actually characteristics through which we quantify bleeding: total amount, rate and duration, total amount, rate and duration, duration. This shows how much would be the volume change, total volume change once the evaporation has taken, once the top water has evaporated. So, how much will be the volume change that would take place. This tells us what is the rate, because initial rate is important. I should have a slow initial rate maybe, and then of course obviously it will be faster. So, high rate of this is the rate, and of course total duration, that is what we mentioned, total duration of bleeding, right. So, that is how we can quantify bleeding. What happens when bleeding takes place? Normal bleeding results in subsidence, although may not be visible in dry and windy situations, because if this dry, lot of evaporation is taking place, if the rate of evaporation is higher than the bleeding rate, then one may not see it, but nevertheless the bleeding is taking place. So, in such situation the reduction in the volume reduction would be taking place. So, normal bleeding results in subsidence, that is most important. This takes place, and therefore, there will be reduction in volume. So, whether you see it or not, there can be some reduction in volume, because in dry and windy situation you do not see it. Dry and windy situation you do not see it, sometime you may not see it. Normal bleeding is also harmful in certain situations, but let us look at a more harmful bleeding. It is a channel bleeding. Channel bleeding is more harmful, it is really harmful, because it will bring latents at the top, resulting in porous internal concrete. So, it will bring large latents, because it is locally there is a channel formation, and lot of bleed material, bleed water will come, and it will bring in lot of cement, because large quantity is coming, it has formed a channel. So, such channel bleeding can result in large latents, amount of latents coming at the top, and therefore, loss of latents from the inside, which means there will be actually porous internal concrete, because material has now come out from inside, and you can have porous internal structure. So, therefore, this is harmful. So, therefore, this is harmful. So, channel bleeding is definitely harmful. Now, excessive normal bleeding is also harmful. Excessive normal bleeding is also harmful. Excessive normal bleeding is also harmful, because it may result in non-uniform concrete. Top will have higher water cement ratio, and bottom will have much lower water cement ratio. A lot of water has come out. So, top will have high water cement ratio. Top layer would be relatively weak layer, okay? And that is why weak plane, it will actually create weak plane at the surface, not planar, weak plane at the surface. So, it will create weak plane at the surface, because the water has come in, water cement ratio is very high, and if some sort of fine latents or water layer has formed at the top, you can allow it to evaporate. If it evaporates, then do finishing, then of course, it is not so harmful. If you are casting another lift on top of it, another set of concrete is being placed on top of it, then the water must dry off, otherwise it will create weak planes, what is called cold joints. So, the construction joints should be weak, the weaker joint should be there. So, of course, a skillful man, a skillful mason would not finish until all the bleed water has actually gone out from the surface. So, it can be harmful, because it can result in non-uniform concrete bringing in some amount of latents, but otherwise just coming some evaporation at the top does not create any some bleed water at the top does not create problem if you allow it to evaporate and then put the next lift and or finishing work you do only after that, then it is not very, a little bit of bleeding is not really harmful to the concrete if it is taken care of properly. In fact, it can reduce down the overall water cement ratio, but such bleeding can be significantly reduced by special mechanized way with controlled permeability, formwork liner, etc., although that is not part of our discussion at the moment, but there are techniques to reduce them, right. So, that is what the effects of bleedings are. Then let us see what are the mechanisms. We have already mentioned that specific gravity of water being lower than other ingredients results in bleeding. Channel bleeding essentially is a result of mechanical rupture of horizontal particulate layer. You see, when water is trying to come out, if the bleeding rate is high, it might cause rupture of the solid system. There a mat like surface layer which is formed, it can cause rupture and take out some material. Once it takes out those material, the channel is formed, and when this materials complete channel is formed, a little bit formed, it can make a slightly bigger channel, and finally a complete channel might form, and through that channel lot of water will have a tendency to come out. So, such channel bleeding is basically rupture of the particulate system or particulate mat that is formed and forms the channel, and that's really harmful, that's really harmful, right. Okay. So, now what people have tried to do, they have tried to look into the bleeding process more, a little bit more in a systematic manner from scientific approach, and one can think in terms of bleeding as a settlement of solids in a suspension of water suspension. Like if you have suspension of water, say soil, not what you call inert solid in a liquid, say soil in water, what happens? The particles, depending upon their sizes, particles try to settle down at the bottom. The coarser particles settle down at the bottom, the finer takes longer time to settle down, and that is governed by Stokes law, depending upon the property of the liquid, viscosity, etc., diameter of the particle and so on. So, one can look in terms of bleeding as a phenomena in which the solid actually settles in a suspension, solid settles at the bottom, gradually, the coarser particle trying to settle earlier, etc., heavier and coarser particle trying to settle earlier, and so one can look at that process in this manner. The other way of looking at it, okay, you have a wet concrete, which is wet system, wet concrete, and in which you have interconnected pore systems created by the water. So, if you have interconnected capillary system, through this water will try to move out, and this is something like flow through pipes as defined by Poiseuille's law. Well, the modification of this Kozny-Karman's equation, which is used in soil, people have tried to model bleeding through this, as if you have a porous system, porous solid system with capillary pores, and through that water tries to come out, through that water tries to come out. So, this is through that water tries to come out, through that water tries to come out. So, this is what is Poiseuille's law. So, there are two ways people have tried to model this system, right. There are two ways people have tried to model the system. So, one way to look at suspension in a solid suspension, the solid is trying to settle down, another way is as if through pipes, capillary pipes, very fine pipes, water is trying to come down. So, that is how people have modeled, and we will not look into the equations in our discussion, but this is how people have tried to model and try to understand the phenomena of bleeding. Well, later the Kozny-Karman sort of equation seems to be more reliable. This is an issue I would like to mention, because it is important from the point of view of aggregate strength and durability. I mentioned earlier that bleed water can get trapped below the aggregate system, bleed water can get trapped. So, the water can get trapped below the aggregate system. Now, this can form water filled pores, and between the water can get trapped below aggregates. Now, this is, for example, this is a water trap, this is another water trap, this is another water trap. So, as the water is trying to come up, it can get trapped below the aggregate system, and this remains porous. So, aggregate and mortar interface are quite often maybe porous because of bleed water trap. Of course, the other reasons are also there, which you shall see later on. This is more porous than the bulk paste, we shall see that later on, but bleed water is an important issue which can leave this as porous, So, this I just specifically mentioned, because this has got some relation to strength and durability. How do we test? Float method. This is the early method which was actually used in research purpose, float method. In this you have simply, in the concrete you have a float. If this is your concrete, let us say, you have a float which will be floating on top, you have a float which will float onto the top. Now, this float is such that it is actually heavier than water, specific gravity more than 1, but less than that of the concrete solid. That means less than the bulk concrete 2.4 or something, I mean, you can think in terms of and combined aggregate specific gravity of solids in case of concrete to be close to about 2.4 or so, or 2. Around that. So, you put a float such that it sinks in water, but floats over the concrete, and then what you do is the bleed water comes at the top. So, this was in the beginning, it will be at the top, and as this settles down, its height of settlement you can measure. Bakelite could be one such materials which actually sinks in water, but floats over solid concrete. So, its subsidence can be measured using this float method. Subsidence of concrete can be measured using float method, and that is what Power used earlier in his experiments, and through which that subsidence diagram was obtained. The ASTM method, which is the other method and being used, is a standard method, is used a cylindrical container, a collecting ring and a burette is placed on top. So, there is a collecting ring and burette is placed on the top of the sample, then carbon tetrachloride is put onto the top surface of the sample as well as in the burette. So, part of the burette is filled with carbon tetrachloride, and this ring actually traps the bleed water and comes into the burette, right, through a funnel, and comes right on top of the carbon tetrachloride. And as the concrete settles, released water accumulates over the carbon tetrachloride and in the burette, and there burette is graduated and where you can measure it at regular intervals. So, that is how one can measure the volume of the water that has come in. This is of course a way of measuring the subsidence. This can measure the volume of water that is coming. That is a standard method ASTM, okay. ASTM, American Society of Testing Material method, and this can be utilized to measure the bleeding. Again, this cannot be a field method, it is mainly meant for laboratory and studies and things like that, right. So, test methods, okay, details of this test method is outside the scope of our work. Let us see how we reduce bleeding. Increasing the fineness of the cement. You see, again, if the cement and paste system and the solid system in the concrete is such that the interstitial pore space between them is very small. So, the capillary sizes are very small, water really cannot come up. If they are not interconnected, then water cannot come up. So, therefore, the basic idea is to reduce down the fineness, if you have increased the fineness of the cement so that the interstitial space sizes are smaller, right, interstitial pore sizes are smaller. You have a finer particles, this space will be smaller. You have a larger particles, this space will be larger. So, cement is the finest particle in the system, and if you have fineness of the cement is slightly high, it will reduce down bleeding. Well, but that may not be possible, it may have other effect, but you can add fine pozzolana to the system and that would reduce down the bleeding. Increase the cement content or cementitious content, that means add pozzolana, fine pozzolana, fineness of the pozzolana and more quantity of this cementitious material will reduce down bleeding. Decrease the water content, too much of water would lead to high capillary system and therefore, the bleed channels can form. If you have less water content, less such water cement ratio, and low water cement ratio will have less bleeding tendency, because capillaries will be relatively less and through which it cannot go. Air entrainment reduces the bleeding. Increasing fines and fineness of the fines again makes the capillary pore sizes smaller, bleed capillary pore sizes in the wet concrete smaller. We are not talking the capillaries in the final hardened concrete, but in the bleed wet concrete itself, the interconnected capillaries should be lesser of diameter and there should be less interconnected, and this is possible if you increase the fines, because the spaces within the fines will be smaller. Increase the cement content or cementitious content, decrease the water content, water cement ratio and slump. Some admixtures like viscosity modifier will reduce the bleeding. Paraffin wax emulsions, they reduce, and bentonite suspension also reduce bleeding. So, these are the means of reducing bleeding, right. Well, I think that would enough, that would finish our discussion on segregation and bleeding. So, today we have discussed two phenomena, one of them is segregation, the other is bleeding. And overall we have discussed in fresh concrete the issues of workability, their measurements, the rheology of cement paste and concrete a little bit. We try to give idea about rheology of cement paste and concrete, and then we have now looked into, lastly we have looked into segregation and bleeding. So, with this we conclude the discussion on fresh concrete. The next turn on next lecture onwards we shall be discussing on strength aspects of concretes. Okay, thank you.